Okay, I want you to imagine something. A world where every continent we know today is just gone. Instead, there's a single, absolutely colossal landmass called Pangaea. For millions of years, that was our planet. And then, it was violently torn apart. Today, we're diving into the titanic forces that ripped that world to shreds and the truly unexpected consequences it had for the entire story of life itself. Let's get into it. So first, a little bit of context. Pangaea wasn't some kind of one-off event. Our planet has actually been doing this for billions of years, assembling and then ripping apart supercontinents in what we call the supercontinent cycle. You know, we've had Columbia, Rodinia, Pantosia. It's this grand repeating rhythm of planetary destruction and creation. But the breakup of Pangaea, that was the cataclysm that forged the world we all recognize today.
And this brings us to the central mystery of the whole thing. I mean, seriously, just try to wrap your head around the sheer, mind-bending energy it would take to fracture a continent, to literally create new oceans from scratch. What in the world could possibly do that? For decades, this has been one of the biggest debates in geology. Was it some violent force erupting from deep inside the Earth? Or was it something more subtle, happening right at the surface?
That entire debate really boils down to two heavyweight contenders, two competing ideas we can call the push versus the pull. Yeah, it's a classic bottom-up versus top-down scientific showdown, all to explain what shattered Pangaea.
So what's the difference? Well, the push theory is pretty much what it sounds like. It suggests a massive force from deep inside the Earth acted like a blowtorch, heating the crust from below and literally pushing it upwards until it cracked. But the pull theory? It argues the action was all happening at the edges, where heavy oceanic plates were sinking back into the mantle, pulling the rest of the continent apart. Kind of like when you yank a tablecloth off a table. So was it a push from below or a pull from the sides?
Let's start with the push. This is the mantle-driven theory. You have to picture a giant, superheated plume of molten rock, bigger than a mountain range, rising up from near the Earth's core. It slams into the underside of Pangaea, forcing it to dome up, to stretch, and eventually to just fracture under the strain. It's the planet's own internal heat engine literally blasting the continent apart. For a long, long time, this was the leading explanation. I mean, it's intuitive, it's dramatic, but is it right?
But then there's the pull, the subduction-driven theory. Now, subduction is just the process where one tectonic plate sinks under another one. The idea here is that at the far edges of Pangaea, you had these ancient, cold, and incredibly dense oceanic plates sinking back into the mantle. And that sinking process acted like a set of massive anchors, creating this powerful, relentless pulling force that was transmitted across the entire supercontinent, just stretching it thinner and thinner until snap! Okay, so how do we decide between them? We've got to hunt for clues in the rocks. And here's where it gets really interesting. If a giant mantle plume, our blowtorch, was pushing up from a fixed point deep below, you'd expect the crack it creates, the rift, to be pretty symmetrical and stable. But the geological data we have from the Atlantic Ocean shows the exact opposite. The split was lopsided. It migrated over time. And that is a huge problem for the push theory.
The pull theory, on the other hand, fits the evidence like a glove. See, we know Pangaea was already moving and twisting around in a really complex way before and during the breakup. And here's the really elegant part. The opening of the new Atlantic Ocean was almost perfectly balanced by the closing of an ancient ocean, called the Tethys, on the other side of the world. So get this, one single mechanism, the pull from that sinking Tethys plate, can explain both Pangaea's weird twisting movement and its eventual breakup. It's just a simpler, more powerful explanation.
So, the evidence really points to Pangaea being pulled apart, not pushed, a colossal tug-of-war that gravity won. But this whole geological drama had a second act, one that would change the course of evolution forever. By tearing the world's land apart, did this planetary catastrophe actually trigger an explosion of life?
Just think about the sheer scale of that transformation for a second. One single monolithic landmass with this harsh, dry interior climate becomes 7 smaller, completely isolated continents. This created thousands upon thousands of miles of new, climate-moderating coastlines. Entire new oceans formed, changing global currents. Each continent basically became its own massive separate laboratory for evolution, where life could now follow its own unique path, totally free from outside competition.
And when we look at the fossil record, well, the result is just astonishing. Look at the bar on the left. Around the time Pangaea began to split, there were about 50 distinct families of land vertebrates. But in the tens of millions of years that followed, look at the bar on the right.
that number skyrockets to over 300. That's a 600% increase. The timing, the correlation is absolutely striking.
It seems like an open and shut case, right? More continents, more isolation, boom, more diversity. A simple and really satisfying cause and effect. But you know what, science? Even the most obvious ideas have to be put to the test. So the next big question became, can we actually prove this link?
How on earth do you test a hypothesis that's 180 million years old? You can't exactly run the experiment again. But with today's incredible computing power, you can do the next best thing. You can simulate it. So a team of scientists set out to build a virtual Earth to see if continental drift, all by itself, could explain that massive boom in biodiversity.
So here's the game plan they followed. First, they built a computational model based on what's called neutral theory, which really just means it simulates the simple, basic mechanics of life. New species arise, they spread out, and eventually they go extinct. Simple. Then, they fed this model the real, known geological history of Pangea's breakup. They hit play and let the simulation run for 180 million virtual years to see what would happen to the number of species. And the expectation going in was crystal clear. As the single supercontinent in their simulation split into many smaller, isolated continents, the total number of species should go way, way up, right? We all know isolation is one of the key engines of speciation. So fragmenting the world's landmass should have a huge positive effect on diversity. That was the hypothesis. And then they got the result. And it was a complete and utter shock. The simulation showed that simply breaking up the continents was not enough. To quote the researchers directly from their paper, continental drift by itself is not sufficient to account for the increase in terrestrial species richness observed in the fossil record. The obvious answer turned out to be wrong.
Now, hold on, it's not that fragmenting the continents is irrelevant. Its role is just way more subtle than we thought. The simulation did show that it has a big effect on creating distinct, higher-level groups, like the families and orders we saw jump up in that earlier chart. But to explain the huge explosion in the sheer number of species, fragmentation alone just isn't the main driver. That simple cause and effect story we all assumed, it's not so simple after all.
So where does all this leave us? We've untangled two major stories. One is geological, about the planet's surface, and the other is biological, about the life on it. And, in both cases, the initial, simple, intuitive explanation turned out to be wrong. And what emerges instead is this much more complex and, frankly, a much more interesting picture of our planet's history.
So let's just boil it down to the key takeaways here. First, the physical breakup. The evidence is pretty clear that Pangaea was pulled apart by sinking plates, not pushed apart from below. Second, the biological consequence. The breakup didn't directly cause the explosion of life, but it absolutely created the conditions for it. It set the stage, and that means other factors, things like the massive shifts in global climate happening at the same time, were likely the primary drivers that acted on that newly arranged stage.
And that, right there, is such a common theme in science, isn't it? We start with these simple, intuitive ideas. A plume pushes a continent apart, splitting land makes more species. But when we actually go and rigorously test those ideas against the hard evidence, the real story is almost always richer, more complex, and way more fascinating than we ever first imagined.
Which leaves us with one final, pretty provocative thought to ponder. The geology of our planet, this slow, epic dance of continents, it only sets the stage for the drama of evolution. It doesn't write the script. So if the physical separation of the continents wasn't the main author of life's incredible diversity, then what was? That's the story science is still working to tell.